Right, good morning, everybody. Can you hear me? Can you see my screen?
Yes, sir. Good morning, sir. You can see you, sir.
All right, thank you. Okay, let's take a moment to scan the attendance and then we shall continue with our class today. All right, let's continue with where we left off in the last class. So in the last class, we have covered something interesting in this topic, which is called K-map. So this is part of topic 4, and I am today we are going to actually wrap up the entire topic 4 and finish the K-map. All right, so topic 4 is all about Boolean algebra and logic simplification, right? So let's just do a quick recap on what we've done. So we started off with Boolean algebra, and we know that by using Boolean algebra, we can actually simplify equations, right? And not only we can simplify equation by using Boolean algebra and De Morgan's theorem and so on and so forth, but we also have another tool that you can use to simplify equations, and that tool is called K-map, okay, or Karnaugh map. And we have learned in the last class how do we use Karnaugh map. Okay, so Karnaugh map is just like a multiple cell that behaves like a map. So I believe I explained to you already. How is it like a map? It is like a map because it's got this wrap around effect. Okay, in the sense that one end of the map is connected to the other end of the map. All right, so we have gone through a couple of example. I think many examples we've gone through. We've gone through 2 variable, like 3 variable K-map, 4 variable K-map. I believe not 4 variable K-map, but we stopped at 3 variable K-map, so we will continue with 4 variable today. But the idea will be the same because the idea that I presented to you guys in the last class is about cell adjacency. So which means cells that are next to one another, you can group them. Okay, and in grouping that, we have grouping the ones, or you can group the zeros. So the difference is that if you group the ones, you get the SOP form, and if you group the zeros, you get the POS form. And I also did like a couple examples in the class, like let's say you have a truth table like so. How do you get this truth table to a K-map, and then to a simplified equation, and then to a logic gate implementation? And I think in your quiz also you have done something similar, right? And we did solve this problem in the class. And we also did equivalent expression using K-map by grouping ones and grouping zeros. So you will find that if you group the ones, you get the SOP form, and you group the zeros, you get the POS form. And these two are equivalent. So in the sense that if you do double De Morgan's theorem, or if you do double negation, if you do double negation on SOP, you get a POS form. Okay, if you do a double negation, here, like so, double negation, and then use De Morgan's theorem to solve it, and you get you get a POS form. If you do double negation here, and you use De Morgan's theorem to solve it, then you would get the other form. So these two forms are equivalent because they are ultimately describing the same truth table. Okay, one is just describing the ones, the other one describing the zeros. Okay, so hopefully that makes sense to you. Okay, so we've also I think we did this example also, how we can make an application using truth table. From the truth table, and then we put the values of the truth table into the K-map, and then at the end of the day, we get a simplified expression from this K-map, right? F equals to something. And once you get that, you can implement them using logic circuits. Okay, logic circuits. So this is your end goal, actually. Simplified expression from the K-map. All right, so today we are going to continue from where we left off. I believe we did at most 3 variable K-map during the last class. And in today's class, we are going to continue on to see what do we have on a table if we have 4 variables. Okay, so let's take a look at this. This is one example. So if you have a 4 variable K-map, the idea is exactly the same as 3 variable or 2 variable K-map. So you want to make sure your group is as large as possible. You want to make sure that there are as few groups as possible. And then you want to make sure that there are no redundant groups around. Okay, remember the a few rules that we talk about when we are grouping ones and zeros. Okay, so this is what we are going to do the same thing. It's just that now we have more boxes to fill in. Okay. All right, so this is one example. Let's go through this one. So we need to use the K-map to simplify the following SOP expression. Okay, following SOP expression, proof using Boolean algebra rule. Okay, you can use De Morgan's theorem 2x, 2 times De Morgan's theorem, or you can call it double negation if you like. So this is the expression. Okay, so if you note over here, this is, what kind of expression is this? This is obviously this is a SOP expression. Okay, is this canonical expression? So to find out, it's really easy. So if you see in this bracket here should tell you all the variables, all the input variables. So in total, you have A, B, C, and D. Those are the input variables. There's no such thing as E or F. So you know that you have 4 variables in total. Now, what we need to do now is to check whether each term has got all these 4 variables. Okay, looks to me that all the term has got 4 variables. So we know that this is actually a canonical SOP. So then it's easy now. To simplify this, you can use Boolean algebra laws, or you can use K-map. But at the end of the day, you should arrive at the same answer. Okay, you should arrive at the same answer. Right. So for this example, we are going to use the K-map as usual. Right. So how do we fill in K-map from this canonical expression? So it turns out it's easy. So all we got to do is just to mark this as the numbers, the logic. So bar means 0, right? Bar means 0 in SOP. So we have 0, 1, 0, 0. So we have 0, 0, 1, 1. This is 1, 0, 1, 1. If you have a pen and paper, I highly encourage you guys to do this so that you're just not watching me. This is how you can get the most from this example. 1, 0. So you have 0, 1, 1, 0. Okay, 1, 1, 1, 0, like that. Over here we have 1, 0, 1, 0. We have 1, 1, 0, 0. I have here 1, 0, 0, 0. Okay, so let's just do a quick check whether to see if there is a mistake somewhere that we are not aware of. 0, 0, 0, 0, 0. Okay, it's okay. This one's okay. This one's okay. 0. This is okay. This is okay. Okay, looks to me there's no obvious mistakes over here. Now we are going to transfer all this value onto this K-map. So the easiest way to do is, of course, you can make a truth table like this, right? A, B, C, D, and then you can put an F like that. Okay, and then you can start to do like 0, 0, 0, 0. Okay, because this is a min term, right? So you have 0, 0, 0, 0, so you got 1 here. Okay, so then you have 0001. What do you have? 0001. Do you have 0001 as a min term? Okay, I don't think so. There's no 0001, so this one is 0 over here. And you can do that until you reach like 1111. Okay, so 1111. Right, I believe it's 0 also. But you can also put this directly on the map without you doing like without writing this on the truth table. So I'm gonna do that right now. So over here we have 0000. So where is it on the map? That is 0000. It is over here, AB and CD. So this is the position on the map, and it's got to be a 1 because this is a min term. Remember, if it's a max term, then you put a 0 on the map. So this one is a min term. I'm going to put a 1 on the map. So the next one is 0100. You can see here 01 and 00. Okay, this is also a 1 over here. All right, the next one 0011. 00, that's on this one. 1 is here. 0011. Okay, great. 1011. You have 10 and 11 is here. 1011. 10 along this row, 11 along this column. Okay. Next, we have 0010. 00 along this row, 10 along this column. This here. 0010. Next, 0110. 0110 is here. 0110. Okay. Next, we have 1110. 1110. This is this one. Next, we have 1010. So we have 10 over here. Okay, we have 1100. Next, we have 1100, which is this one. I have 1000. 1000. Okay, so this is the map that we get over here. Of course, the remaining ones, they are obviously the max term, right? And the max terms, they are all zeros. I'm gonna fill in this map completely with zeros. Okay, so that is the filling in. Now, here's the interesting part. How do you get the group out of this map? Okay, so first, let us apply the same rule again. So we want to group the largest possible value of 1. So what's the largest possible value of 1? You can group 16 ones together, or if you go one level lower, it's got to be 8 ones together. If you go one level lower, you can go 4 ones together, and you got to group 2 ones together. And the last choice, if you got nothing to group with, of course, you can group the individual one together. Okay, so we go from the largest possible to the lowest possible. Okay, so let's try with 16. Is there any way we can group 16 ones together? Because the maximum number of boxes over here is 16, right? It is impossible because there are some zeros here. There's no way we can group all 16 ones together. So this is not possible. Now, is there a way we can group 8 ones together? So I can see like 1, 2, 3, 4, 4 ones over here. And is there 8 ones that are connected to each other? Anyone can see it? Okay, so if you remember the wrap around effect, so this end of the map is actually connected to this end of the map, right? So do you see what I see over here? So we have 4 ones over here. We could have grouped them like this, 4 ones, and then like 4 ones like this. But we know that these two groups are actually connected to each other because they are at the end of the one is at the end of this map, one is at the beginning of this map. So what I can do is do this. This one is one group together. This one group. So there you go. That's your first group. And okay, so we got one groups of 8 over there. So what is this expression for this group? Let's write this down now because it's going to be cluttered later. So the green group would be, so now we're going to go hopping cells and to see which are the variables that doesn't change. So we're going to say, okay, let's check for A and B. So if I am this cell, A and B is 0, 0, A and B is 0, 1, A and B is 1, 1, A and B. So obviously, if I hop cells like this, the value of A and B changes all the time. Okay, here to here, the value of B changes. Here to here, the value of A changes. So A and B is not going to be in our equation. What about C and D? Okay, let's try to check variable C. Okay, if I hop from this cell to this cell, 0, 0, 0, 0, it's still 0, 0 in this cell. In fact, wherever I go in this, as long as I'm in this column, the value of C and D changes. But then if I hop over to this cell, the value of C changes, right? The value along this row, along this column, the value of C is 0. But as soon as I hop over to this box, the value of C becomes 1. So the only value that does not change is D. Agree? The only value that does not change. So if you do a check over here, what's the value of D in this box? 0. What's the value of D over here? 0 also. What's the value of D over here? 0. Value of D over here? 0. What's the value of D over here? It's still 0. Value of D here, here, and here, they are all 0. So D is the only variable that does not change, no matter how many boxes you hop around this group. Okay, so I'm going to write down D. Now the next question, is it D or D bar? Right? It's going to be D bar because the value that we talk about is 0. The value that is not changing is 0. It's going to be D bar like that. Okay, that is the green color group. Now let's take a look at what's the next group that we can put together. Okay, so we see that there are still ones out there. There are still these ones out there. So we cannot stop grouping here. So we only stop grouping when these two ones are included in one of this group. Okay, so now we're going to find the next group that's going to include these two ones. Okay, so what do you say? We try again. Like 16, is it possible? It's not possible. 8, is it possible? I don't see any way we can group it in groups of 8. Okay, so not possible. Now 4. Can we try to group these two in groups of 4? I think we can. So we can do this like that. And remember, the end of the map is connected to the end of the other side. Okay, the end of one side is connected to the end at the other side. So what we can do here is like so. Okay, like so. Then, is there any other ones remaining out there? No. So we can stop our grouping here. So which means that no more grouping after this. Now, what's left to do over here is to get the expression for the ones. that is in this purple group. So now let's go hopping boxes. So if I'm in this box, the value of A and B is 0, 0. If I hop over here, the value of A and B is still 0, 0. If I hop over here, the value of A and B is 0, 1. If I hop over here, the value of A and B is still 0, 1. So what's the variable that's not changing? So I see the variable A changes. If I hop here to here, A changes from 0 to 1, but the value of B does not change. So just do a quick check. If the value of B over here is 0, the value of B over here is still 0. The value of B over here is 0 again. The value of B over here is 0 again. So the value of B does not change no matter how much I hop around this purple group, in this purple group. So the question is it B or B bar? So because I am associating this B with this value of 0, say 0 here, 0 here, 0 here, and 0 here. So it's got to be B bar. Okay, now what about C and D? Does the value of C and D change? Okay, let's check. So we check here, the value of C is 1, the value of C is 1, the value of C is 1 also, the value of C is 1. Oh, great. The value of C does not change no matter how much we hop, right? Okay. So which means we need to write C like that. Need to write this is grouping ones, we got to write this way, C. Okay, now question is it C or C bar? Okay, it's got to be C because the value that is not changing is this 1. Okay, so any question on how I get this expression so far? So far so good, right?
Yes, sir. So far, so
Yes,
good,
sir.
sir.
So far, so good.
Okay, thank you. So what's the final expression then? So the final expression would be, okay, let me go back to that. So the final expression would be the addition of all the equations that you get from this group. So over here would be B bar and C plus with B bar. Okay, so this is what you have as your final answer. Okay, and from here, what you can do is, of course, like once you get this simplified expression, you can draw the logic gate diagram. Okay, if you're in a real project, then you can put your order. You can go out and buy these components, these logic gate components, and start to connect them together. Okay. All right, that is K-map for this question. For variable K-map, I don't see it as a very different. I don't think it's very different from all other variable K-map, but most of the time you would see 4 variable K-maps than 3 or 2. I don't think 2. I have ever given any 2 variable K-map as a question because it's too simple. Okay, so I've got the answer on this one here. For this map like that. Okay, this one I did that as the answer. So you can refer to this later on. But of course, my scribbling here is going to be gone the moment I exit this slide. All right, so I'm going to modify this question a little bit now, just to make sure you guys can understand the 4 variable key map, right? So let's say I want, can you group zeros over here? You can group zeros over here. So what do you have if you group zeros over here? You have this 4 group over here like that. Let's just try to group the zeros. And you will find that you get the POS form. Okay, so you can group zeros like that over here. And then there's a POS expression from this. And you can also group zeros like that over here. And then you get another, and at the end of the day, your expression will be a POS expression. And then you can get this POS expression by doing double negation, and then you get this one. Okay, so if you do double negation on this, you get a POS expression, and that will be an expression that for the groups of zeros. All right. Okay, any question on this example? Otherwise, we'll move on to the next one. Okay, if there's no question, then let's take a look at another one. Right, let's take a look at how we solve this one. Express the expression of f equals to this long expression in sum of min terms using K-map. Okay, then determine the minimal SOP form of the expression. Find the equivalent SOP expression in the post form. Prove your answers using K-map and De Morgan's theorem. Okay, this is exactly what we have been doing so far. All right, so I'm not going to do this full example over here because this is the same as the previous example. I'm going to outline to you how do you do it, and then this is the final answer. And once you're done, you should get this one as your answer. You can double check it over here. Okay, first, what do you have? You have this f expression. Okay, so this expression, okay, maybe I should write this much more clearly. This is f, a, b, c. So you know that we have three variables. Okay, we have three variables over here. So the first thing you want to do is, okay, you see that you have this, and this. They are not in the canonical form. So what you want to do is to make it into a truth table. A, B, C, and then F. So you start from this, okay, all the way down to 1, 1, 1. So get the truth table out for this expression. Okay, so you can do this. The straightforward way is to put in all these values over here, 0, 0, 0. You put in into this equation, and then you compute what is the value of f. Okay, let's say f is 1 over here. And then you input 001 into this expression, and you get something over here, maybe 0. Okay, this is an example, okay? This is one way of doing it. The second way of doing it is you get the mean term out of this. Okay, so from this over here, if you make it into a canonical SOP, then you would get in everything, all the terms over here, they are representative of the value, right? So over here, if you add a b, if you add a variable b inside here, you add a variable c inside here. So this one is c, this one's complete, and you add a variable a inside here. So once you get a canonical expression, then it will be like what we did just now. So you can just say, like, for example, over here we have 101. So we know that 101. So we have 101 over here. It's gotta be a 1. Okay. You do this for this. You do this for this, and you do this for this, and then that's how you can fill in the truth table. That is step 1, getting the truth table out, whichever method that you use. There are also other shortcut methods online. So I highly encourage that you guys go and research how do we get the truth table just from using this without doing this canonical SOP and without inputting this one by one value. So there are methods to do that without going through two of this. I encourage you to explore that yourself. But the answer will be the same. The truth table you get will be the same. Right. So once you get the truth table, then next is the matter of transferring this truth table to a K-map. So you can do like something like this, and it will be exactly the same like what we had done. Okay, transferring this value into this table, and then once you get that, you can group them. Once you group them, you can get the depending on which one you group. If you group the ones, you will get the SOP expression when you group ones. Okay, ones. And if you group the zeros, you will get the zeros. If you group zeros, you get the POS expression. Okay, so you can try to group both, or you can group this one first, get the SOP expression, and then you convert them using double negation. That works. Or you can group ones and then get the expression, and then you got group zeros and you get another expression. Okay, and to double check that, we do the double negation. Right. So exactly what you need to do in this one. So I'll leave it to you to complete this example. All right, so next example over here. So right now I believe I've covered everything that you need to solve all these examples. Right now I'm not solving this by myself one by one, step by step anymore, because I think that'll be boring to you guys who already know how to solve it. Now I'm just outlining the steps that you can take for you to solve all this. Okay, so this one as well, and I'm showing you how the the different perspective that the question can bring, can present itself. All right, so over here we have another example, yet an example with this f a b c d. Okay, you have all this variable in this term. This is a POS term on a K-map, and so map this into a K-map and determine its min-term and max-term list form. So again, I have the answers over here. So all I want you to do after today's class is to verify that you can get the answer based on what the steps that I am going to tell you. Okay, so this one is the same as the previous example, except this time we have, instead of SOP expression, we have a POS expression. So is this a canonical expression? I don't think so. It's not a canonical expression because this term is missing B, this term is missing A, this term is missing A. So now, because it's not a canonical expression, now we need to find a way how to make it canonical in order for us to get the truth table. Okay, so we can get the truth table out as usual using this traditional way. You take all the values and you input them into this expression and you get a value of f, the end. The other way around is, of course, you can make this into a canonical post expression. So we did this example in the class. How do we make a normal POS, normal post expression into a canonical post expression? So once you get the canonical post expression, then you can do then you can map this out into the K-map directly without having actually to do this truth table. Okay, so remember, if you are doing this post expression, now what you would get is from this truth table as well. So you get, for example, you get like that, right? This is an example. So what you want to map on this K-map is 1 or 0. You are dealing with zeros, remember? Okay, so if you're dealing with posts, you are dealing with zeros. Okay, so this is the max term that you are going to get over here. So it's going to be here 0, 0. Yeah, it's got to be 0 over here, 0, 1, 2, 3. Okay, so once you got all the zeros over here, then you can start grouping the zeros together, and then you can get the simplified form. Okay, of course, in this question, it didn't ask you to get the simplified form. So the question just stops at here, min term and max term lists. So this is the final answer for this question. But usually, when you get the min term and max term list, the next logical thing to do is to get the simplified version. Okay, simplified. Simplified in this case is post, and in this case is simplified SOP expression. Okay, so I leave it to you for you guys to do this example. Okay, so before we move on, I want to highlight over here also in case some of you are wondering. So let's say this is another example that's unrelated to this one. Okay, I just crossed my mind. Let's say if we have a group like this, do you think we can group them in any way? It looks like it's separated at the 4 corners of the map, right? But we know that the 4 corners are actually connected together. So this is an interesting one. You can group it like this. And these are actually groups of 4 ones. 4 ones together. Okay, this is an interesting example of a map. And of course, what else do you have? Yeah, I think that's what I thought about from last semester. We did this one together. Okay, this is about this example. All right, so now you might think that, okay, what is a good application for this K-map? So you can simplify. So with this K-map, now you have the power in your hands to simplify any Boolean expression. So just give any Boolean expression with a number of variables, 1 variable, 2 variable, 3 variable, 4 variable, 5 variable even. You can use K-map to simplify them. Okay, so and this is one example. This is one example where you can use K-map. So I believe that you have come across this device in, if you're doing lab, you might have come across this device. Okay, so this device is it's a 7-segment display driver. You can call it driver, or you can call it decoder. Okay, some people call it different names. Okay, but it's this thing. It's driver IC. So what this driver IC does is it takes in 4 variables as input, and then from that 4 variables, it is going to translate into lighting up certain segments of the LED. Okay, for example, if we get the value of 0, 0, 0, 0, so let's say this is a value A, B, C, and D. Okay, now we are going to light up this segment, here, here, and here. Okay, all except G. And if we get the value of 0001, then we are going to light up, I believe, this B and C. Okay, and so on and so forth. So this is the truth table going to be like. Right. So this is the truth table going to be like. So we have 0, 0, 0, 0. Okay, just take a look at this. This is, okay, let me just draw this line as this is the input. And this inputs, and these are the outputs. Okay, so these are the inputs, and these are the outputs. On the left, inputs; on the right, outputs. So if you have zeros, all zeros together, now we want to make sure that A, B, C, D, E, F, they're all light up except for G. So double check over here. If A, B, C, D, E, F, they're all logic 1 because we're going to light them up except for G. Okay, now we do the same for 0001. Everything is a 0, so everything is turned off except the segment B and the segment C. Okay, so we do that for every single value over here until we reach 1001, because 1001 is 9. After 1001, there's no 10. Okay, right? So the maximum value that you can put on this 7-segment display is 9, right? So after 9, there is no more possible value. So it's 0 to 9 only. That's why you see this truth table there. It's only up to 1001. Okay, what happens to the rest? We'll talk about it after this. The rest is not even listed out here, but the rest it's still part of the truth table. Okay, let's go back to this truth table. It's just a partial truth table because it's 0000 until 1001. So how do you get the circuit for this? So the circuit is that previously we have always done truth table for just one output. Okay, remember we've done the truth table for okay, something like this. So we've done truth table just for one output, all inputs, and then just one column of output. So what if we have multiple columns of output? So we can have multiple maps. Okay, this is what I'm going to show you over here. You can have multiple maps. So this map for so you can have one map for output A. You can have for A. Okay, for A, so the map would be this value 1011, and you can start filling in this one 1011, and then so on and so forth until you are full. And then like you have another map for B, and then for C, and then up until G. Okay, up until like G. So you have all the maps, and at the end of the day, you're going to take all this expression, and they all add up together. Okay, you're going to combine all this expression, and that expression, from that expression, you get logic gates. Okay, and that is the logic gate that is inside this thing. Okay, so over here, I am just illustrating an example of how you actually design an IC. Okay, an IC that is going to take in the value of inputs and then translate them into the value of 7-segment display outputs. Okay, so inside here, there's actually a bunch of logic gates that is constructed using KMap. Okay, this is example application, 7-segment decoder or 7-segment driver. Okay, so we've talked about 1 variable to 4 variable keymap, and of course we can also have a 5 variable keymap. I don't see this very frequently, but it's again the same thing. Okay, so I highly encourage you guys to explore this. This might come out in your assignment, this might come out in your projects as well. So I highly encourage you to explore. And how do you do a 5 variable keymap? So the trick is easy. It's the same as what we have done so far. Nothing has changed except that the number of boxes on the map, they are significantly more. Now we have 32 boxes on the map. And I've also attached this video. So this video is something that you can watch to guide you. Of course, like there are other videos out there that can do the explanation better than this, but this is one that I find useful. So please do not be limited by the things that I say in the class, by the things that I show in the class. So I want to remind everyone that knowledge is out there. The thing that you are learning in this class is the same as the people in Harvard, in Oxford, in MIT. I've checked the syllabus and they are the same. So you can actually take their materials and learn it also. So this is actually what I hope you do, all right? Because then you know that, oh, actually I am learning something that's on par with students from other top universities. Okay, and I sometimes also take reference from their syllabus into what I have on my slides. All right, so do not be limited again by what I show you here. It might be, I think it's better if you can explore these ideas on yourself, on your own. All right, so that is about KMap. Any question so far about KMap? Oh. No issues? Okay, so right now we are going to cover the last portion of this topic, and then we'll wrap up and we'll end this we'll finish topic 4. All right, so this is one condition in the KMap where we call it as a don't care condition. Okay, don't care condition. The name is interesting. All right, so let's take a look at what this thing is all about. Okay, so these are the expression. Okay, so the logical sum of the minterm associated with the Boolean expression specifies the condition under which the function is equal to 1. The function is equal to 0 for the rest of the minterm. Okay, whatever that means. You can digest them later on. Okay, however, there are applications where the function is not specified for a combination of the variables. Okay, so this is what I want to highlight. The function is not specified for a certain combination of variables. For example, what we've seen just now. Okay, so in this example, so we have 0000 up to 1001. So for this combination of outputs, right? For this combination of inputs, we have specified exactly what is the output going to be. But what about this? 1010. This truth table does not tell us what is the output of 1010 going to be. So what exactly is the output of 1010? Because we need to complete the truth table as well, right? So this is where we talk about don't care. So for 1010, because 1010 does not result in anything over here. If you have 1010, you give it to a display driver, it will not show you anything. So this is what, or maybe it will show you some random numbers. Okay, so you can try this on your display IC if you're in the lab. Right, so this is where we talk about don't care. So we have 1010, so we do not specify what the output is going to be. We don't specify this output A, it can be 1, it can be 0. Okay, this is where we put in X into the keymap, and this X is known as a don't care. Don't care means we do not specifically say the output is 1 or 0. Okay, so let's take a look at some concrete examples later on. Okay, so these unspecified mean terms, they are called don't care conditions. Okay, because we don't care what the values are. Right, let's take a look at okay, so don't care condition can be used in the K-map as well to provide you simpler to provide you your K-map with a simpler expression. Okay, and the don't cares are usually marked with X or marked with D on the K-map. Okay, and it could take on any values. Okay, so remember, don't cares can take on value of 0 or it can take on value of 1. Okay, it does not matter. Let me show you through this one example over here. Suppose you have this expression like this. Okay, so you have A, B, C. Okay, simple one. And okay, we have min terms over here, 2, 3, 4, 5. Okay, so let me just mark this 2, 3, 4, 5 on the map. 0, 1. So you have 2, 3, and then you have 4, 5. Okay, like that, right? 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. Okay, so let's suppose that this thing is not here right now. Let's just ignore this, right? Now, let's try to group this first. So if we are to group this, how would you group this? Groups of 4, is it possible? I don't think any of this group of 4 is possible over here. So the only way is for us to group this like so. Okay, let's find out what's the expression for this group. So we have expression like so over here would be, so I'm going to write here A, B, and C. So we have over here A bar, like that, and then we have B. Okay, so over here we have A, what else? B bar. Okay, variable of A is not changing. The variable of B bar is not changing. Okay, A bar, B, A. Okay, so this is how we would group things. Am I right? Yeah, I think there's no problem. Okay, this is how we will group things if we don't have this don't care. Okay, so the expression would be like so A bar and B plus A and B bar. But now if we include this, okay, let's include this don't care into this K-map and see how is it going to make a difference. So don't care 6 and 7. So let's go 0, 1, 2, 3, 5, 4, 5, 6, and 7. Okay, so what it means for don't care 6 and 7 is that for this cell 6 and 7, the output does not matter. It is not going to affect the behavior of your truth table. So that's why we don't care whether this value is 0 or whether it is a 1. Okay, so how can we make use of these don't care values in this K-map? Okay, obviously these are zeros over here. You cannot change this because if you change this zeros over here into a 1, then your truth table will change, right? But for this value over here, don't care. If you change this, it's not going to change your truth table. Now we are going to see how can we make use of this don't care over here to make our expressions simpler. Okay, here's what we can do. Because we don't care this x is 0, 1. Now we are going to put this x to our advantage. Okay, so instead of putting this as an x, I am going to assume this as a 1 instead, like that. Take this as a 1. Is this an advantage? Do you think in this situation it is an advantage to us? I would say yes, but why? Because now we have a larger group. You know that when you have a larger group, then your expression can be simpler. Okay, let's try to see what this expression turns out to be. Now we can group it like this, and we can group it like this. Okay, so from this expression, you get A. From this expression, you will get B. So your outcome, your simplified expression will just be this. Compare that to the ones above. The previous one we didn't consider the don't care. Okay, we only consider the min term. Now in this example, the green one, we consider min term as well as we make the don't care a 1 so that we can be it can be advantageous for us when we try to group things so that this can be simpler. Then again, are we actually changing the truth table or not? We are not changing the truth table, right? Why? Because we are only messing with this don't care values. Okay, now is that clear what the don't care does? Okay, so there's an answer over here, A plus B. So obviously, you can make this don't care other values as well. Okay, so let's say right now, right, I want to make this. If I make this just this don't care a 1, and if I make this don't care a 0, do you think that is advantageous to us? This is the case, right? If this don't care is a 1 and this is a 0, so how would you group this? You would group this like this, you group this like this, and then you have a ones like this. So you end up with 3 groups, and you know that with 3 groups, of course, the expression is going to be much more complicated. So making this don't care, this value is not going to be it's not going to help us. Okay. What about if you make this a 0 and you make this a 1? Okay, same thing. Now you have to group it like this, and you have to group it like this right now. So you have 3 groups again. Okay, it's not going to be helpful if you make that don't care a 1. So if you make this, what if you make this 0 over here? You make this 0 over here, it will be just like our original group, like that. You would end up with this blue color equation, right? So the don't care values are there for you to change so that your groupings can be made more simpler, like so. Okay, so that is it about don't cares. Is there any question on don't care? No question? Okay, very well. Okay, so now this is another example, yet it is the same thing. So we have min terms given. Okay, not in all questions you get this min terms conveniently given. Sometimes the question will just give you an expression. From that expression, you get the min terms, right? So for the sake of this example, that is, I'm giving you the min terms and then also the don't cares. So over here, I am going to show you what you can do, and then I leave it to you to solve the entire thing. So we have over here a list of min terms and a list of don't care. So the first thing what we can do is to map this min term and don't care onto the map. Let's do that right now. So if we do this min term, so 0, 1, 2, 3, so that is 1, 3, 4, 5, 6, 7, 7, 8, 9, 10, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so we have over here, let me double check my, yep, let me double check this answer. 0, 1, 0, 1 is here, 2, 3 is here, 4, 5, 6, 7 is here, 8, 9, 10, 11 is here, 12, 13, 14, 15. Okay, so it looks like our min terms are right on the map. Okay, so what about the don't cares? So we have 0, 2, and 5. So zeros, I'm just going to mark this as X. Zeros. Okay, let me change this in color so that it's more visible. So the don't cares, I'm going to put in this color. 0, 1, 0, 1. Okay, 0, 1, 2, 3. So that's 0, that's 2, 4, 5. 0, 5. Okay. So these are all the min terms and the don't cares on the map. And obviously the rest are the max term. So let me just put in the max term. Max term, these are all the max term. Max term, max term. Okay, so now we want to simplify the following. Okay, so now you want to simplify, it means that you can choose to group zeros, or you can group ones if you like. Okay, in this example, let's try to group the ones. Okay, you can do this for zeros if you want. Okay, so Now, how do we group this? Let's try to group this. Okay, so if we look at this situation over here, so what is the possible group over here? So the possible group over here, see, is this. That is one large group. What is another possible group that will include this guy in? I can do this like that. But if I were to consider the don't cares in, can I make the don't care work for me to make this simpler? I can. So I see that over here there's a one lonely one outside here. What if, what if I put this don't care, because don't care does not change any value, does not change the truth table. What if I make this don't care into a 1? Because that I can get this as a group, and that will make my expression simpler. Okay, get what I mean? I can do that. That is one option. The other option is also, of course, like there are two other don't cares over here. I can also make this into a 1. I can also make this into a 1, and then I will get a group like this. So I have two groups of 4 ones. That will make my expression simpler. Okay, that is how I make this don't care work for me. But if I choose this as my solution, this don't care, I don't mess around with this anymore. Okay, and I'll get one expression for this and one expression for that. Okay, that is how we make the don't care work for us. Okay, is that clear? Okay, so let's suppose if you want to group zeros. Okay, let's suppose you want to group zeros and you want to make this don't care work for you. So let's see how that works. Let's suppose you want to group zeros. Okay, we see that there are 4 zeros over here. There are 4 zeros over here. Okay, now these 2 remaining zeros, what do I do with them? I can group them like this 4. Okay, so there are 3 separate groups of zeros. Is there a way I can make this don't care to reduce my number of groups? Okay, if I make this don't care 0 over here, does that make it a difference? If you put in a 0 over here, then you can group with 4 zeros like this, but then it still doesn't reduce the number of your groups, right? So in this event, you see that this don't care is not going to help you. It's not going to do us any good, even if you put it as 0. Okay, so let's just make this don't care 1 then, so that we just put it as don't care. We don't touch this don't care, and then this group of zeros just like that. Okay, if you're grouping zeros, what I'm trying to show you here is it's not going to help reduce your number of group if you're grouping zeros. But if you're grouping a 1, then you can make this don't care. You can take this don't care to be a value of 1 so that you can reduce the number of groups. Okay, so that is how we use the don't care to our advantage. So this will be the answer. Yeah. Oh, okay. I see. Okay, I see something that I think I missed out this one. Okay, so actually, if you want to group zeros, you can make the don't care to your advantage. Okay, so this is something I didn't see just now. Okay, if you make this a 0, right, like that. Okay, now this time you can group it like this, and you can group it like this. Okay, and then okay, in this case, if you put it like this, then this don't care is helpful for you to group zeros. Okay, my bad. Just now I didn't see this possibility. Okay, just as I said, like grouping this is like an art. So you got to imagine, can you group it like this or like that? Okay, so sometimes even I will miss out groupings if I don't look into it carefully. Okay, so now if you put this don't care as 0 over here and 0 over here, it definitely helps you reduce the group. So previously we had smaller groups, but we have many of them. So right now we have one giant groups of 8 zeros over here and one group of 4 zeros. Okay, so only 2 groups, and then we have a larger group, so which is going to make your expression simpler. Okay, so this is my answer. You can refer to this answer when you're trying this out at home. Okay, I highly encourage you guys to try this out. And yeah, that is it about don't care. Any question on don't cares? Okay, there's no question. If there's no question, then there's one more subtopic that I want you guys to study. It is the subtopic of implicants. Okay, so I want you guys to find out what are implicants. And I've also attached one video here that could be useful for implicants. Of course, I will continue to post other videos as well that I think will be useful. So I highly encourage you guys learn this implicants, what it's all about, and learn as much as you can. And maybe in the next class we'll have a quiz or something on implicants. Okay, I'm not sure yet. I'm still trying to evaluate whether or not we need to have this quiz. Okay, all right. If there's nothing else, then I will end my class here today. So this is the attendance if you came in late. And if there is no any other question, thank you so much again for attending our class today. And it is again the end of our, it's almost the end of the week again. So, and today we are finishing this topic 4, and next week we are going to dive in topic 5. So hopefully things are right now clear about topic 4. Topic 4 is, as I said, one of the most important topic in digital logic. If you can understand just one topic, I'd say take topic 4. So understand this topic very well, because it's going to help you not only in this course, but it's going to help you in your future course. All right, so hopefully things are clearer, and I will end my class right here. If you have any other questions, please feel free to stay back and I'll answer your questions. I'll guide you through your questions as well. And as usual, after this, I'll post either assignment or either a quiz for topic 4. All right, thank you everyone. Have a great weekend and stay safe. Take care.
Thank you, sir. Have a great weekend, sir.
Thank you, sir.
All right.